right now. You see skin, you see texture, you feel the warmth of your blood, and you assume it is solid. You assume it is real. But what if I told you that what you are seeing is just a user interface? What if the feeling of touch is just a collision variable being calculated by a processor so powerful we mistake it for the laws of physics? Today we aren't just asking if we live in a simulation. We are going to look at the source code. We are starting right here with the biggest question a human being can possibly ask. We are looking at the simulation hypothesis. This isn't about robots taking over or some sci fi movie plot. This is a rigorous look at physics as a computational process. The core idea we are exploring today is simple yet terrifying. It suggests that reality as we know it, every star, every atom, every thought, is actually a computational substrate. It means the universe is a machine processing information. When we say computer game, we don't mean a toy. We mean a system that follows rigid rules, updates in discrete time steps, and renders information only when necessary. This hypothesis suggests that matter is just data. It suggests that energy is just the cost of processing that data. Over the next hour, we are going to strip away the illusion of a smooth, infinite reality. We are going to look for the pixels. We are going to hunt for the lag. We are going to see if the universe has a refresh rate. If reality is a simulation, it has to have limits, it has to have shortcuts, and if we look close enough, we might just be able to see the machinery working behind the curtain. Here is exactly how we are going to break this down. We have a long journey, so we need a map. We are going to move through 8 specific stages of understanding. First, we need to meet the idea in plain English, stripping away the academic jargon to see the core concept. Then, we are going to look for bits. We need to understand how a computer fakes reality using zeros and ones and how that scales up. After that, we will look at the software stack. Just like your laptop has layers of code, the universe might have layers of physics. We will hunt for bugs. If this is software, there are going to be errors. We will look for cosmic lag and chunky space. We will do the mini math. We are going to calculate exactly how much RAM you would need to simulate a single galaxy. We will compare real data against fake data to see if our universe matches the checklist of a simulation. We will be honest about what we can't prove. Finally, we will end with a guide on how you would build your own universe if you had the power. This is a step by step deconstruction of reality. Let us start with an apple. On the left, you have a real apple. If you bite it, it has taste. If you leave it out, it rots. It is made of roughly 10 to the power of 19 atoms. That is a staggering amount of data. Every single one of those atoms has a position, a spin, a charge, and a momentum. To simulate that apple perfectly, you would need to track every single one of those data points simultaneously. Now look at the right. That is a game apple. It looks like an apple. It reflects light like an apple, but it is hollow. It has no atoms inside. It doesn't rot because of bacteria. It rots because a line of code tells the texture to change color after a certain amount of time. This is the core difference. In the real world, properties like smell are complex interactions of volatile organic compounds hitting receptors in your nose. In a simulation, smell is just a trigger. It is a simplified command that says if player is near, trigger apple scent. Weight in the real world is mass times gravity. In a simulation, weight is just an arbitrary number assigned to an object. The danger level for a programmer, the difficulty to code this, is low. The hardest part is the quantum fuzziness. A real apple has quantum uncertainty. A game apple just approximates this with noise. The question we have to ask is, does our universe look like the complex apple on the left, or does it show signs of being the simplified apple on the right? If we find that physics takes shortcuts like the game apple, we have a clue. To understand the universe as a computer, you have to understand the bit. A bit is a switch, it is off or on, 0 or 1. This is the fundamental building block of all information. You group 8 of these bits together and you get a byte. With a byte, you can represent 256 different values. That is enough for a rudimentary alphabet or basic colors. Scale this up. Take 24 bits and you can define 16.7 million colors. That is enough to trick the human eye into seeing a smooth gradient. Now look at a 4K television screen. That screen is updating roughly 1.4 billion times every second to show you a moving image. It feels real, it feels fluid, but it is just a grid of numbers changing very fast. The universe might just be this same principle on an infinite scale. Instead of red, green, and blue values, the universe tracks mass, charge, and spin. A star isn't a burning ball of gas in this model, it is a collection of data points on a three-dimensional grid. The universe simulator would need to handle infinite complexity, adding depth, time, smell, and gravity as calculable variables. If you zoom in on a star in a simulation, you aren't seeing continuous plasma. You are seeing quantized brightness levels, just like pixels on a screen. But the pixels are so small, we haven't found the edge yet. If the universe is running on a computer, that computer needs hardware. We can use our own technology as an analogy to understand the cosmic computer. You need RAM. This is the workbench. This is the temporary storage for the pieces of the universe that are happening right now. You don't load the whole universe into RAM, just the parts that are active. Then you need the CPU. This is the thinker. The CPU handles the logic. If you drop a ball, the CPU calculates how fast it falls. It processes the decisions and the rules of physics. Then you have the GPU, that is the artist. The GPU is responsible for parallel rendering. It decides how light bounces off water. It handles the visuals. But here is the catch, you cannot store every atom, it is too inefficient. The universe would crash. So you use compression. Instead of defining every single blade of grass with its own unique atomic structure, you make one perfect model of a blade of grass. Then you copy and paste it a billion times. You rotate it slightly, maybe stretch it a bit, but the core data is the same. This is optimization. This saves memory. You see this in nature all the time. Electrons are all identical. Every electron is exactly the same as every other electron. This looks a lot like an optimized object class in programming code. It saves resources. We have a problem. The universe is big. The amount of data required to simulate the observable universe atom by atom is impossible. Let us look at the scale. One emoji is 4 bytes. A photo is 3 million bytes. A human cell is 10 terabytes. That is just one cell. The observable universe contains 10 to the power of 80 atoms. If you tried to store the position of every atom in the universe on hard drives, you would run out of matter in the universe just trying to build the hard drives. Even if you turned every atom in the universe into a storage device, you wouldn't have enough room to store the universe itself. This is the simulation problem. This tells us something crucial. If this is a simulation, it cannot be a perfect simulation. It cannot simulate every atom all the time. It must use shortcuts. It must use clever optimizations. It has to cheat. It has to compress data. It has to delete things when you aren't looking. This impossibility of scale is actually our first clue. We couldn't look for perfection, we should look for the pixelation that comes from saving space. We should look for the glitches that happen when the computer runs out of a memory. Every video game has a config file. This is a simple text file that sets the rules before the game starts. The universe seems to have one too. We call them the fundamental constants of nature. Look at the speed of light. It is exactly 299,792,458 meters per second. Why that number? In a simulation, this acts as a maximum speed limit. If things moved infinitely fast, the computer couldn't render them. It would crash. A speed limit keeps the processing load manageable. Then look at the gravitational constant. This value determines how hard gravity pulls. If you tweak this number in the config file, stars would act differently. Lower it and you can jump over buildings. Raise it and you are instantly crushed. The value of pi is fixed. The rules of arithmetic are fixed. You cannot change these while inside the game. They are locked. We also have Spatial dimensions equal to 3. Up, down, left, right, forward, backward. Why 3? Why not 4 or 10? Because 3 is the most efficient way to render a complex volume without melting the processor. And time flow equal to forward only. You can't go back. This looks like a strict logic rule to prevent database errors. If you could go back and change data, the simulation would desynchronize. These constants aren't just random numbers, they look like parameters chosen for stability. So, how do you organize space in a computer? You use a grid. Imagine the universe is a giant three dimensional spreadsheet. Each cell in this spreadsheet is called a voxel. It's like a 3D pixel or a Minecraft block. If you tried to store a voxel for every point in space, you would crash the system. Most of space is empty, it is just vacuum. So you use sparse storage. If a block is empty, you don't save a huge file saying this block is empty. You just write a 1 or a 0, a single bit. Is there stuff here? No. Done. You move on. You only spend memory on the blocks that are actually have matter in them. If a voxel has a planet in it, you allocate a dense storage, 256 bits or more, to describe that planet. If it is empty, it costs almost nothing. This technique saves a factor of 1000 times or more in memory usage. This is exactly how we program massive open world games today. We only render the chunks of the map that matter. The universe might be a grid where the Planck length, the smallest possible measurement of length, is just the width of one of these voxels. Programmers hate writing the same code twice. They use libraries. A library is a collection of pre-made assets that you can pull from. The universe seems to have a very small particle library. There are only about 17 fundamental particles in the standard model. You have the electron, photon, quark, gluon, Higgs boson, and a few others. That's it. Everything you see from a star to a sandwich is built from just these few ingredients rearranged. Think about how efficient that is. The file size for an electron template is tiny. It has a specific mass, a specific charge, and a specific spin. That data is smaller than a text message. It is smaller than an emoji. Once you have that template loaded into memory, you can clone it zillions of times for free. You don't need to redesign the electron for every atom. You just point to the reference in the library. This explains why every electron in the universe is identical. They are all instances of the same class. This elegance saves massive amounts of memory. If every particle were unique, the universe would be unsimulatable. Computers work in cycles. Tick tock, calculate, update, calculate, update. The universe has a heartbeat like this too. We call it Planck time. It is a tiny slice of time, roughly 5.39 times 10 to the power of negative 44 seconds. This could be the tick of the simulation clock. In every single tick, the universe runs a loop. Step 1, check particles. Where is everything? Step 2, calculate forces. Gravity pulls, electromagnetism pushes, the strong force glues quarks together. Step 3, update positions. Move everything to its new spot based on those forces. This loop runs 10 to the power of 43 times every second. That is a refresh rate so fast that reality looks smooth to us. But it is still discrete. It is still a step-by-step process. To save power, the simulation uses shortcuts. It only checks nearby friends. If an electron is in your finger, the simulation doesn't need to calculate how it interacts with an electron in a galaxy far away. The force is too weak. It ignores it. This is like chunk loading in Minecraft. By ignoring distant, weak interactions, the simulation cuts the number of calculations from an impossible number down to a manageable one. It prioritizes the local environment. This is one of the wildest ideas. In a video game, the computer does not render the world behind your head. It only renders what the camera sees. This is called frustum culling. The simulation hypothesis suggests the universe does the same thing. This is the observer-centric model. The distant universe, the stars and galaxies billions of light years away, might not be fully rendered three-dimensional objects. They might just be low-resolution background images, points of light, 1 kilobit of data per second. As you get closer, the detail increases. Your local environment, your room, is medium detail. Molecules and surfaces are calculated, but the close-up reality right in front of your face is rendered in 4K. Atoms are simulated only when you look at them with a microscope. This is like streaming a video on YouTube. If your internet is slow, the quality drops. The simulation saves bandwidth by not rendering the 10 to the power of 80 atoms that no one is looking at. It creates a reality that looks 4K when you focus on it, but is blurry and compressed where you aren't looking. Telescopes, telescopes are just tools that request high detailed data from the server. When we point a telescope at a blurry star, the simulation says, oh, they are looking, and quickly generates the high res details. You know how games auto-save at checkpoints? The universe might have a mechanism for this. It is called quantum measurement. In quantum mechanics, a particle exists in a superposition. It is in many places at once. It is a wave of probability. It hasn't decided where to be. But the moment you measure it, the moment an observer looks, the wave function collapses. The particle snaps into a single, definite position. In simulation terms, this collapse is a right to disk operation. While the particle is unobserved, it is just a probability equation in RAM. It is cheap to calculate. When you observe it, the simulation is forced to commit a specific value to the hard drive. It creates a checkpoint. Player saw the electron here. This explains why the quantum world is so weird. The universe is delaying the heavy calculation until the very last millisecond when you force it to give you an answer. This minimizes the file size of the universe. The estimated save file size for the universe is huge, so the system avoids saving, that is collapsing the wave function unless absolutely necessary. If space is a grid of voxels, then space is not smooth. It is chunky, it is pixelated. If you zoom in far enough, you should see the jagged edges of the blocks. We can't see this with our eyes, but we can test it with high energy particles. Cosmic rays are particles flying through space at nearly the speed of light. If space is a smooth slide, these particles should be able to travel at any energy level. But if space is a staircase, a grid of distinct blocks, then eventually a particle will have so much energy that its wavelength becomes smaller than the step size. When that happens, the particle should stub its toe on the grid. It should crash into the geometry of space itself and lose energy. This predicts a strict speed limit for cosmic rays. Guess what? We found one. It's called the GZK limit, Grayson-Zapptem-Kurzman limit. We see a sudden drop off in high energy particles exactly where the theory predicts they would crash into a discrete grid structures. This cosmic ray wall could be the signature of the grid. It is physical evidence that space might not be continuous. Let us talk about the lag. In a game with a low frame rate, fast moving objects don't move smoothly, they teleport. They jump from point A to point B because the computer missed the frames in between. If the universe has a refresh rate like Planck time, then light itself acts like this. Light moves very fast. If we measure the speed of light with extreme precision, we might be able to catch the jittering. We might see it speeding up and slowing down slightly as it waits for the next tick of the universal clock. Historically, our measurements of light has gotten more and more precise. In 1675, we used Jupiter's moons. In 1849, we used tooth wheels. Today, we use atomic clocks and lasers. We are getting to the point where we can measure the speed of light with mind-blowing accuracy. If we detect a tiny fluctuation, a jitter that shouldn't be there, that should be the evidence of the simulation's tick rate. It would prove that time is not discrete. Time is actually discrete, not continuous. We are searching for the frame rate of the cosmos. When game developers build a massive sky, they don't draw every cloud by hand. They use tiling. They take a texture and repeat it. If you look closely at the floor in a video game, you can see the pattern repeating. We are looking for this in the sky. The cosmic microwave background (CMB) is the afterglow of the Big Bang. It is the oldest light in the universe. It should be random. It should be chaotic, but scientists have found strange patterns. They have found spots in the CMB that look identical to other spots. We are talking about 10-degree wide patches of the sky that match perfectly. The statistical statistical chance of this happening naturally is less than 0.001%. It is incredibly unlikely. It looks like someone copy pasted a section of the sky to save time. It looks like a repeating texture. We use satellites like Kobe, WMAP, and Planck to take higher and higher resolution photos of this baby picture of the universe to see if these patterns hold up. If they do, it suggests the universe was procedurally generated using repeating tiles. Symmetry is beautiful, but in computer science, symmetry is efficiency. If a butterfly is symmetrical, you only need to store the data for the left wing. Then you tell the computer, mirror this for the right wing. You just saved 50% of your storage space. The universe is obsessively symmetrical. We have charge conservation, we have parity, we have isotropy. The universe looks the same in all directions. Space is measured to be incredibly flat with a margin of error of 0.002. This too good to be true. Perfection is suspicious. Why is the universe so perfectly balanced? Why does the math work out so cleanly? In the simulation hypothesis, symmetry is a compression algorithm. It reduces the number of unique variables the system needs to track. Fewer if statements means a faster game. Perfect scores on these physical tests might mean the teacher copied the answer key. It suggests the laws of physics are optimized code designed to run efficiently, not random chaos. This is the ultimate showdown. Digital versus smooth. Digital means there is a smallest unit, a pixel. Smooth means you can zoom in forever and never hit a limit. We are trying to probe this with the Hughes Driver experiments. We use extremely precise probes to look at the energy levels in atoms. If space is a digital grid, like the Minecraft stairs, then as an atom moves, it should experience tiny bumps as it moves from one grid cell to another. This would cause a microscopic shift in its energy levels. So far, the results are smooth. We haven't found the grid yet down to 10 to the power of minus 27 meters, but the Planck scale is at 10 to the power of minus 35 meters. That is much smaller. The grid might still be there, just hidden deeper than our current microscopes can reach. Or the simulation might be using anti-aliasing, a graphics technique that blurs the edges of pixels to make them look smooth. Quantum uncertainty might be that blur filter, disguising the grid from our eyes. We have a database of things that don't make sense. In a game, we call these bugs. In science, we call them anomalies. Take Tabby's star, it dimmed by 22% randomly. Stars don't do that. Dust doesn't do that. Is it a rendering error, a missing texture? Take fast radio bursts, FRBs. These are millisecond blasts of insane energy from deep space. They happen in patterns. Are they data packet losses? Is it a lag spike in the server? The wow signal in 1977 was a massive burst of radio waves that never repeated. Was it a debug message left by a developer? Then there is the expansion of the universe. It is accelerating. We call it dark energy, but we don't know what it is. In a simulation, this looks like a scaling issue. Maybe the developer tweaked a parameter and now the map is stretching. Even Oumuamua, the interstellar object, moved strangely, accelerating without gravity. Was it a non-player character, an NPC, glitching out? Science is the process of debugging reality. When we say something is unexplained, it just means we haven't found the line of code that causes it yet. To understand these scales, you need to visualize the powers of 10. You cannot just use numbers. Our brains don't work that way. Start at 10 to the 0, that is 1, that is you, a human. Go to 10 to the 2, that is a comic book, 100 pages. Go to 10 to the 3, a large village, 1000 people. 10 to the 6 is a city, a million people. 10 to the 9 seconds in 32 years, a billion. 10 to the 23 is the number of stars in the observable universe. This stack helps us realize that we are trapped in the middle. We are too big to see the atoms, 10 to the negative 10, and too small to see the edge of the universe. We need to get comfortable with the fact that our intuition fails at the top and bottom of this stack. We need to trust the math, not our eyes. Energy is just a number in the simulation. Let us compare the values. 1 joule is the energy to lift an apple by 1 meter. 1 electron volt EV is the energy of a flea jumping tiny. An AA battery has about 5000 joules. A candy bar has 1 million joules. The Hiroshima bomb was 6 times 10 to the power of 13 joules. A supernova is 10 to the power 44 joules. So remember the GZK limit, the cosmic ray cutoff is at 5 times 10 to the power 19 electron volts. That sounds small compared to a supernova, but for a single particle, it is like a baseball thrown at the speed of a jet plane. That is the energy limit of the grid. If a single pixel contains more energy than that, the simulation says stop. It clamps the value to prevent an overflow error. Time is granular. A human reaction time is 0.2 seconds. To us, that feels instant. A camera flash is 1 millisecond. A computer clock ticks every 1 nanosecond. Atomic vibration is 1 femtosecond. Planck time is 5.4 times 10 to the power of negative 44 seconds. If the universe updates once per Planck time, that means there are 10 to the power of 43 ticks every second. That is a number larger than all the grains of sand on earth. Catching a missed tick or a dropped frame in the universe is incredibly hard because the frame rate is billions of times faster than our eyes. We are watching a movie in ultra super fast motion and trying to see the gap between the frames. Here is a way to understand pixels using sound. You can do this at home. Step 1. Load a song into Audacity, free audio software. Step 2. Zoom in. Keep zooming. Step 3. Eventually, the smooth wave becomes an staircase. You see the dots. These are the digital samples. Step 4. Measure them. A CD player plays for 44,100 steps per second. To your ear, the music is smooth. The steps are too fast to hear. But the steps are there. The cosmic scale is 10 to the power of 30 times smaller than those audio steps. We are trying to hear the pixelation of reality, but the resolution is so high it fools us completely. Despite the digital steps, the illusion of smoothness is perfect. If we wanted to simulate a universe, how would we code it? We would build a physics engine. We would define objects, create clone of particle. We would set position to random x, y. We would create a loop, forever loop, move speed steps. We would add logic, if on edge, bounce. This is exactly how basic simulations work. We store positions at x and y coordinates, pixels. We store time as ticks. We calculate forces like gravity. The computer runs this math every frame. We create a micro universe that generates measurable physics. It has friction, speed reduction, it has collisions. A stick figure inside this simulation would think the bounce rule is a law of nature. They wouldn't know it is just a line of code we wrote. Can we detect lag at home? Here is a theoretical experiment using an Arduino concept. Light takes time to travel. If the simulation lags, light might arrive late. Setup: you need a laser pointer, a mirror, and a photodiode sensor connected to an Arduino. Process: you shine the laser at the mirror. It bounces back to the sensor. You measure the time. You record 100 drops, pulses of light. You look at the histogram. Most pulses arrive instantly, but maybe, just maybe, you see a consistent 1 millisecond offset, a lag spike. Interpretation: now, in reality, a 1 millisecond lag is usually just your wiring or the atmosphere. But if you could isolate all those variables and still found a delay that shouldn't be there, that would be the external tick. It is a fun way to think about how scientists hunt for these signals, even if a tabletop version is too crude to find the real Planck delay. Let us look at the data cost of life. A single human cell has about 10 to the power of 14 atoms. If you store the position, x, y, z, velocity, mass, and charge for every atom, you need about 256 bits, 32 bytes. per atom. Total bits 3 times 10 to the 16 bits. Raw storage needed 4000 terabytes for one cell. That is a stack of 1 terabyte SD cards taller than Mount Everest just to store the blueprint of a single cell. It is inefficient, but if you use smart encoding compression, you can shrink this. You use a reference library. You don't store the electron data every time. You just say electron at x comma y. You compress the repetitive patterns with aggressive compression like video game sprites. You could shrink that 4000 terabyte down to maybe 4 gigabyte. This confirms that if the universe is a simulation, compression isn't just an option, it is a survival requirement for the system. So how do you store a galaxy? The Milky Way has 400 billion stars. Naive storage, storing every star individually, would take 10 to the 69 bytes. Impossible. So we use 3 tricks. Difference storage. Don't store the whole star. Just store how it is different from the average star, like ratio 100 is to 1. Star types. Group stars into 8 fundamental types. Repeat the templates. Ratio 100,000 to 1. Procedural generation. The holy grail. You don't store the stars at all. You store a seed. A seed is a math rule. You plug the number Tokyo into the algorithm and it generates a city map. You plug a number into the universe algorithm and it generates a galaxy. With procedural generation, you don't store the galaxy map. You generate it on the fly when the player looks at it. This brings the storage cost down from 10 to the 69 bytes to just 10 to the power of 14 bytes. That fits on a modern petabyte server rack. You just compress the universe into something you can hold in a data center. Computing isn't free. It costs energy. This is known as Landauer's principle. Every time you erase a bit of information, like overwriting a memory address, you generate heat. You must release energy. The minimum energy to erase one bit is roughly 3 times 10 to the power of negative 21 joules. If the universe is simulating 10 to the power of 80 particles, updating 10 to the power of 43 times a second, the power consumption is colossal. Total power required 3 times 10 to the 102 watts. Our sun produces 4 times 10 to the 26 watts. You would need 10 to the 75 suns just to power the processor for our universe. This is called impossible energy barrier. Unless the simulators have reversible computing, a theoretical tech that uses zero energy to switch bits or access to an energy source infinitely greater than our own universe, a classical computer cannot run our reality. It would melt. This suggests the computer is running on physics we can't even comprehend. A perfect simulation hides its mechanism. It is like a magician's trapdoor. If you can see the trick fails. We have models that try to explain the weirdness of quantum mechanics by suggesting there are hidden variables, hidden code we can't see, like superdeterminism. Everything is pre-recorded. There is no free will. The outcome of every experiment was written in the code at the Big Bang. Detectability approximately 2%. Many worlds with fake branches. The simulation creates decoy realities to handle probability. Detectability approximately 1%. Extra dimensional coder realm. The computer exists in a dimension outside our 3-dimensional space. We can never probe it because we are stuck in the screen. Detectability approximately 0.5%. The key insight is this: absence of evidence is not evidence of absence. Just because we haven't found the trapdoor doesn't mean it isn't there. Scientists are just building better detectors to find the seams in the stage. It gets deeper. If a civilization becomes advanced enough to build a simulation, they will run millions of them, and inside those simulations, the simulator people, that is us, might eventually build computers, and then we build a simulation. It is a stack, a nesting doll. Base reality, then simulation level 1, 2, 3, and so on. This is the probability argument. There is only one base reality, but there could be billions of simulated realities. Statistically, what are the odds we are in the one real base reality? Almost zero. It is far more likely we are in one of the billions of simulations. If we find a glitch, we prove we are in a simulation. If we don't, we just keep looking. But the math suggests we are likely digital. So, what is next? We have four frontiers to push to find the truth. Faster computers. We need exascale computers to simulate our own complex physics. If we can build a matrix, it proves it is possible. Better clocks. We need optical lattice clocks to detect those minute temporal fluctuations, the ticks. The bigger telescopes. We need next generation arrays like LISA to see the cosmic structures with finer resolution. Quantum sensors. We need to probe the fundamental forces. Projected gains are massive. By 2035, neutrino detectors will be 100 times more sensitive. By 2050, quantum clocks will be 1000 times more stable. We are rapidly approaching the resolution limit where the pixelation of the universe should be visible if it exists. So, in the end, asking if the universe is a game doesn't make it any less real. If you feel pain, if you feel love, if you taste the apple, it is real to you. But knowing that there might be code underneath the surface changes everything. It means reality isn't a solid, unchangeable rock, it is a process, a calculation. And if it is a code, maybe just maybe one day we can learn to read it. Keep looking for the glitches.